Hello dear friends, welcome to the lecture of ordinary differential equations. We are studying differential equations of first order and first degree. In our last lecture we have studied what is exact differential equation and the condition, necessary and sufficient condition for the exact differential equation, and if it is exact, so what is the working rule to find the solution. That part we have studied in our earlier lecture. Now the equation, every equation of this form m dx plus n dy is equal to 0 will not be exact, and if it is not exact, some equations of this type can be reduced to exact form with the help of integrating factors. Now what is meaning of this integrating factor, that we shall see. So therefore this type of equation is equations reducible to exact form, which is not exact but can be made exact with the help of integrating factor. So the meaning is, if this equation m dx plus n dy is equal to 0 is not exact, and if it becomes exact on multiplication by some function u, suppose u of x and y, then the function u is called an integrating factor, or in short we shall denote it by if. So it is a function of x and y only. So u is a notation, or in short we shall say the integrating factor is if. If is the integrating factor. Now we have considered here one example. The differential equation y dx minus x dy is equal to 0 is not exact. So why it is not exact? Because if this is compared with this form m dx plus n dy, what is m? M is y and n is minus x. See, comparing these values. And what is the condition for exactness? Partial derivative of m with respect to y, which is 1 here, must be equal to partial derivative of n with respect to x, which is minus 1. And you see these are not equal, and therefore this equation is not exact. But it can be made exact by multiplying this equation by a function of x and y, and that function is we say integrating factor. Now if you multiply this equation 1, if we multiply 1 by, say the factor I shall consider as 1 upon y square, then it becomes, now this is we are considering as integrating factor. So multiply this to the equation, or the equation given equation becomes y dx minus x dy divided by y square. Multiply by 1 upon y square means we are dividing it by y square is equal to 0. Now this is exact differential. So how? Because it is differential of, that is d of x upon y is equal to 0. So what is d of x upon y? We should note that or observe that how to find the total differential of function of x and y. We have to use the usual rule of derivative, d of x upon y, or that means the quotient rule we have to use. And by quotient rule we are writing some of the differentials here also. So here the same we have written, and how to write it as by quotient rule, that will be see d of x upon y will be equal to, the denominator is y square and the numerator is denominator into derivative of numerator, that is here we shall say differential. So y denominator into differential of numerator, that is dx, minus numerator, that is x, into differential of denominator, that is dy. In place of derivative we say differential, and we write d. Differential of x as d of x, differential of y as d of y, and which is the same as y dx minus x dy divided by y square. And that means this expression is a total differential of x upon y, and therefore the equation becomes exact by definition. When we say the equation, given equation is exact if it is differential of some function of x and y, and this is differential of now x upon y, but not original equation. After multiplying by y square, 1 upon y square, that means dividing by y square, the equation becomes exact, and thus here 1 upon y square is an integrating factor. Now what is the solution of this? The solution on integration is easy to write, that is integrate this. Integration of d of x upon y is only x upon y and a constant of integration. So its solution is on integration x upon y is equal to c, and thus here 1 upon y square is an integrating factor, is if of equation 1, integrating factor of 1. Now the next question is whether the integrating factor is unique. How many integrating factor will be there? And now we see one factor we have considered as 1 upon y square. Now instead of 1 upon y square, if you multiply 1 by 1 upon x into y, say multiply 1 by 1 upon x into y, and the equation 1 becomes, or we get y dx minus x dy divided by x into y. Now what about this? So this can be written as, now see, we can separate the parts of the numerator, y dx divided by xy, and this y cancels, it becomes dx upon x minus x dy divided by xy. X divides out, what remains is dy upon y is equal to 0, and this is exact. So why this is exact? Because we can integrate this. Dx upon x is actually d of log x, and dy upon y is d of log y, or integrating we get so we get log x, this is first, minus log y, and the constant we may see, we may consider in log c, and after simplifying we will get the same answer that this implies on simplification. The solution is log x minus log y is log of x upon y, and that is equal to log of c, means x by y is equal to c. So earlier the answer may be y upon x is equal to c, that is reciprocal, and taking reciprocal of a constant is again the constant. So the solutions are equivalent or the same. So thus 1 upon xy is an integrating factor. Therefore 1 upon xy is also an IF, integrating factor of 1. And one more thing we can say, as 1 upon x square also is integrating factor. Further, if you multiply 1 by we get that will be y dx minus x dy divided by x square. But to express this as differential of a quotient, we can write the negative sign separate, and then we write this term first, x dy minus, or yes, x dy minus, and this will be minus y dx. See, actually the value is not changed. We have taken negative sign common from this, and this term is written first, this minus of minus becomes plus. And why this is written so, interchanging the term? Because now this is equal to minus of d of y upon x. See, by quotient rule, d of differential of y upon x is, denominator is x square, and now what is the numerator terms, that is denominator x into differential of numerator, that is dy, minus y into differential of denominator, that is dx. So it is exactly same as this one, and thus this is the exact differential equation, and its solution is, so this is equal to 0, right side is 0. See, the right side is 0 of 1, and by integration or on integrating it gives minus y upon x is equal to a constant. So on integrating or on integration, minus y upon x is equal to c or minus c can be taken, and y upon x is equal to c is a solution, is the solution, general solution. And thus what we observe is that for a given differential equation which is not exact, can be made or can be reduced to exact form by multiplying it by a function of x and y. We have denoted that function by u. Here what we have observed, u is equal to, first we have taken 1 upon y square, next we have taken 1 upon xy, and next we have taken 1 upon x square. These are u functions, that is integrating factors. And after multiplying the given equation by integrating factor, the equation becomes exact, and that means the equation is reduced to exact form, and that can be easily solved. Or so if you get the total differential directly, then we can integrate. On integration this d cancels. We know integration of dt is t plus c. So likewise integration of d of y upon x is y upon x. Negative sign is separate, and constant of integration we have taken in negative sign, and thus these are the integrating factors. And one should note that there are infinite number of integrating factors for a given equation. So we can write that as a note. There are infinitely many. Here we have seen 3 factors, but if you see mu is a factor, then the given equation after multiplying this equation, after multiplying mu by mu, becomes mu into m dx plus n dy is equal to a sum total differential, that is d of u. And again if that function is multiplied by a function of u, that also becomes integrating factor. So the number of integrating factors of this equation m dx plus n dy is equal to 0 is infinite. That means there is no not only fixed integrating factor, there may exist infinite number of integrating factors. Now the question is, to reduce the given equation in exact form, we require integrating factor. Such a function, on multiplication by that function, the given equation reduces to exact form. Now how to obtain the integrating factor, or how to get the integrating factor so that the equation becomes exact? So there are different methods or rules to obtain integrating factor. Now first of that is to find integrating factor by inspection. So by observing the given expression or the given equation, or in the equation observing the values of m and n and rearranging the terms, we can express the equation in exact form, and that method is known as integrating factor by inspection. For that purpose we should know some exact differential of standard functions by using the formulae of differentiation, and that we shall first write, and then we will solve examples on it. So first I have written the d of x into y. The rule of derivative is to be used, that is derivative of product. X into y, we know what is d by dx of u into v, that is u first function derivative of second, and plus second function derivative of first. So likewise instead of writing the derivative we have to write the differential, and therefore d of x into y will be x into differential of y. First function differential of y. Instead of derivative we say differential of y, and differential of y is written as d of y. Differential of x is written as d of x. Total differential of u will be d of du, etc. So this is the first term, x dy plus next second function as it is, y into dx. So this much is the d of xy. If we have the expression of this type, we can directly write this as d of x into y. Now what about this d of x upon y? We have used that result here in this example, earlier example, and here we have to use the quotient rule of derivative, d of u upon v, and we know what is the rule of differentiation for u by v. D by dx of u by v, we write this as the denominator is square of this function v, numerator is v denominator into derivative of numerator, that is du by dx minus u into dv by dx. So this is the derivative of quotient, and using the same rule we have to write d of x upon y, and for that purpose we write the denominator as y square. Instead of u and v, here are x and y, and denominator means y first, v, y, and now don't write d by dx etc. We write d. So differential of numerator, here derivative of numerator, here we say differential of numerator, that is dx minus, and now the numerator, that is x, into differential of denominator, numerator into derivative of denominator, here numerator into differential of denominator, that is dy. So this is d of x upon y. Now likewise we can have what will be d of y upon x. I have not written that, but you can see what is the d of y upon x, and that can be written easily by interchanging x and y or using the same rule independently. So that will be, say, x square x dy minus y dx. So this is also to be remembered. So it is exactly same, interchanging x and y we can get this, and therefore I haven't written this. So what is the differential of x square upon y? Using again the quotient rule. So this will be y square at the denominator, and the numerator will be y, that is denominator, into differential of numerator, that is du by dx. We have written earlier the quotient rule. Quotient rule we have to use, that is denominator differential of x square. Now what will be differential of x square? Differential of x square will be actually this is x square derivative, we know it is 2x. So we have to write 2x into differential of x. So this is to be remembered, or this is to be noted, how to write differential. D of x square is 2x derivative of x square with respect to x into differential of x. So it is 2x dx, and that too I shall write here x dx minus numerator, that is x square, into differential of y, that is dy. So this is d of x square upon y. Now what will be d of y square upon x? Just interchange x and y. That will be the denominator will be x square, and it is 2 again 2xy dy minus y square dx. And now differential of log of xy. So we know that differential of log of x is 1 by x dx. Derivative of 1 log x is 1 by x multiplied by differential of x. And it is clear that if you write this dx here, then that will be d by dx of log x is equal to 1 upon x. But instead of x here, it is xy. So we have to use also the chain rule. So it is 1 over xy, means xy is at the denominator, and into we have to multiply by derivative of inner function, that is differential of x into y. But what is differential of x into y? That we have written here using product rule, that it will be x dy plus y dx. So this much is d of log of xy. And next is derivative or differential of tan inverse of x upon y. Now what will be d of tan inverse x? by the formula. Derivative of tan inverse x is 1 upon 1 plus x square, and here it is d, so we have to multiply it by dx. So d of tan inverse x is 1 upon 1 plus x square into dx. Instead of x, it is x upon y. So we must have to use the chain rule. First it will be 1 upon 1 plus x upon y whole square into differential of d of x upon y, and this is to be simplified. See, I shall simplify it here and then write the value there. See, we can write this d of x upon y, this value y dx minus x dy. So therefore that will be, so I shall remove this and write it here. So multiply the numerator and denominator by y square, then that this is y square, this y square and that y square divides out, and therefore what we shall get is here as 1 upon, or this expression y dx minus x dy divided by, yes, divided by x square plus y square. You can check it, putting this value second here and simplifying, multiplying by y square at numerator and denominator, and this y square cancels. So this is the expression. Now next I have written was the function d of minus 1 upon xy. And what is the derivative of reciprocal function? We know d of 1 upon x. D of 1 upon x is minus 1 over x square by the rule of differentiation. Power function rule can be used, and similarly this will be, but there is a negative sign, negative of negative. This again reciprocal function's derivative becomes negative, so that negative and this negative becomes positive, and that is 1 upon x square y square into differential of xy by chain rule. Differential of xy is this one, so it will be x dy plus y dx divided by x square plus x square into y square. Or you can use the quotient rule. See, x square y square is the denominator, numerator will be x into y into derivative of differential of 1, that is 0, minus of minus 1 becomes plus 1, and differential of xy is x dy plus y dx. So that is the differential of minus 1 over xy. Next can be taken as d of x square upon y square, or y square upon x square, and that is, see, use the quotient rule only, and that is y to the power 4 square of this, then y square into differential of x square, that we know 2x dx, minus x square into differential of y square, that is 2y dy. So this much is d of x square upon y square. Interchanging x and y, we can write d of y square by x square. See, this is 2x square y dy minus 2y square x dx divided by x to the power 4. So thus we have written some expressions. Now what we shall consider is next as d of e power x divided by y, differential of this, and differential of that will be by quotient rule again, that will be y square at the denominator, y into differential of e power x, that is e power x into dx, minus e power x into differential of y, that is dy. So these are few terms that we have written. Now whether anything remaining is, so what about log of x upon y, differential of log of x upon y can also be taken. So these are not only specific, but this for example we have written these exact differentials. So if I write this as d of log of x upon y. So what will be this is 1 over x upon y will be y upon x into differential of this. Differential of x upon y will be y square and then y dx minus x dy. So at the most we can write this cancels this y with y square, and this can be written as y dx minus x dy divided by x into y. So this is differential of log of x upon y. So here we have written differential of log of x into y. So these are the sum of the differential for example we have written. So in the given example, if such type of expression occurs, so that means if this type of expression we obtain, then we should come to know this is total differential of log of xy. So this actually we have came across with this type of expression, and that we should recognize it as a d of tan inverse of x upon y, or this expression is d of minus of 1 upon xy, that we should express. And this is by inspection. By inspection we have to collect the term and put these either one of these forms in total differential form, and then the equation will be exact and the equation can be integrated. Now we shall solve some problems on it. Now we shall solve some problems to reduce the equation in exact form. And here what is important is to find the integrating factor, and these problems will be depending on integrating factor obtained by inspection. Or that means actually we should not obtain integrating factor separately. We are not multiplying this equation by a function which is called as integrating factor, but we are rearranging the terms only. Rearrange the terms in such a way that the equation becomes exact. And to rearrange the terms, we shall make use of the earlier results, the total differential results we have written. Earlier 8 results we have written. Now we solve the first problem. See, this is the given differential equation, and whenever it is a function of x and multiplied by dx, that becomes exact. So here we see it is x power 4 into e power x, and that is entirely function of x multiplied by dx. So we should write this separately. But here it is function of x and y, and this is also function of x and y, and this is differential of x, differential of y. So I shall write the given differential equation is or can be written as x power 4 into e power x dx. And next is, this is negative sign, this we should write separate, and in that also we can observe that m can be taken common, and I shall write this term first. See why this is to be done. So we will write this first as it is. M only common, I shall write m common plus, and then in bracket what remains is minus 2x y square dx and plus 2x square y dy is equal to 0. This we have written, taking m common. And why not other terms are taken common? But you see, we have this type of expression there, differential of say y square upon x square. What is the result we have written earlier by quotient rule? This will be the square of the denominator, means x power 4, and denominator, that is x square. Differential of the numerator y square, that is 2y dy, and minus sign is there, minus numerator, that is y square, into differential of the denominator x square, that is d of x square is 2x dx, and that can be written as minus 2x dx. See, this is a differential of y square upon x square, and such type of terms occur here. 2x square y dy, here it is dx, 2y square x, you see, 2y square x dx and 2x square y dy. We want this term positive first and this term second. So interchange the terms and divide by x power 4. So dividing by x power 4, we get, see, this will be e to the power x dx plus m, and I shall write this term first according to this. That is in bracket I shall write 2x square y dy minus 2x y square dx. Don't take any term common from this because it is there, it should be there in the expression, and we are dividing by x power 4 here. This divides out, 1 remains, and divided by x power 4 in is equal to 0. And because the bracket is d of y square upon x square, so we can have this as e power x dx plus m d of y square by x square is equal to 0, and thus this is exact. So because this can be easily integrated, or this is actually d of e power x, total differential. This is also a total differential and this is a total differential, and this is exact, so we can integrate exact differential equation. Thus here the integrating factor by inspection means we have only to rearrange the terms, not to find any other function which is a external function to be multiplied. Only the rearrangement terms reduces the equation in total differential form or exact form. So integrating, we get this, what is integration of, I shall write directly, what is integration of e power x dx, that is e power x, and plus m is a constant, and integration of this differential, that is only y square upon x square, and is equal to constant of integration. Integral of dx is x, integral of dt is t. So similarly, integral of d of any function will be that function. Integral and derivative, these are inverses of each other, the effect cancels and this function remains only. So this is the general solution, or this can be simplified, multiply throughout by x square, that is x square e power x plus my square is equal to cx square. This is the general solution. And thus we should express the equation so that it becomes exact differential equation. Now solution for the second problem. Here also the given differential equation is y dx minus x dy plus log x dx is equal to 0, and that we can observe y dx minus x dy. So that can be written in total differential form. We have two quotients here, that as d of y upon x or x upon y, that you should note, but we can consider y upon x, d of y upon x. And what is the differential of this? We have written earlier, the denominator is square of x dy minus y dx. Now you see x dy is the second term, y dx is the first term, but we can interchange the terms. Taking minus sign common, this may be written as positive. Why this is written, and why not d of x upon y? So if you write this as d of x upon y, then that will be y square y dx minus x dy. So it is actually this is exact form, this form, but we will not make use of this. Why? Because here to get this form we have to divide by y square, and if we divide by y square here, we have to divide this term also by y square, and this is a function of x. This should be entirely in terms of x to make it as total differential, and if we divide by x square, then this will be in this form. Yes, and if we divide by x square, that is again a total differential. So that is actually we are discussing the third example, and I want to leave this third example for you to solve. So you should solve this example, third example. This is not the second, this is the third example I am discussing. So this what we should do is, I shall write one step and then you can solve. See, the divide by x square. Dividing by x square, what we will have is minus sign common, and this I shall write this first, x dy minus y dx divided by x square, and plus log x divided by x square means log x into x to the power minus 2 dx, and that is equal to 0. Now this is negative, d of this will be y upon x, and plus this is log x as it is, log x into x to the power minus 2 dx is equal to 0. Now you see this is exact differential equation. Why? Because this is a total differential form, and here it is entirely function of x and into dx. So this can be integrated. So we have to integrate this. Integrating this, what we shall get? Integrating this will be minus y upon x and plus integral log x into x power minus 2 into dx is equal to constant of integration, can be written as c. Now how to integrate this function? So you should use the integration by parts. The rule that to be used is integration by part, and the first function as it is, integration of second, etc. So I hope you can further solve this, or see, if you do few steps, then the solution will be obtained like this. Then you should solve second and fourth yourself. So this is minus y upon x plus, and inside bracket I shall write log x. Integration of this will be x power minus 1 divided by minus 1. Power function formula. I am writing directly minus integration, derivative of first, that is 1 upon x, and integration of second, it is again x power minus 1 divided by minus 1 dx is equal to c. So this is minus y upon x plus it is minus log x upon x, and then next is this minus and this minus becomes plus. So yes, plus, and what is the integration of 1 upon x, that is x to the power minus 2 dx is equal to c. And finally this will be minus y upon x minus log x upon x, and plus the integration is x power minus 1 divided by minus 1, that minus sign I have written here, and is equal to c. So we may multiply by x, and we'll get the minus x we shall multiply, and this gives the answer as y plus log x, and multiplying by x, that gives minus plus 1, y plus log x plus 1 is equal to cx. So which is you see yes, cx plus y plus log x plus 1, y plus log x plus 1, and plus cx, this term is taken on this side, or that for that purpose we can consider this constant as minus c. Constant can be taken in any form, and to adjust the same form of the answer, we take the constant as minus cx, and that is minus cx, and you shift this term on this side, you will get the same answer, cx plus y plus log x plus 1. So this is actually we have solved third problem. So I wanted to leave this for you to solve. Now you solve the second and fourth problem yourself at home, yourself. So that second is easy. You can see the variables can be separated. For the second, I shall write the answer here. So answer for second is, just a minute, the answer for second is x square y plus e power x is equal to cy. This is the answer for second. So you solve this second problem. We have solved 1 and 2. You should solve this second and fourth yourself. Here also you should try to separate the variables. So trial and error method can be used. Shift the terms, observe the earlier results, and some of the forms the total differential can be obtained. And after obtaining the total differential, integrate it to get the answer. So this is about some problems on writing the expression by inspection, obtaining or finding the total derivative by inspection. Remaining part we will continue next time. Thank you.